So for the direction of a vector, well, so that has to do with the angle with reference to the x-axis, right? So, and in this case, well, not surprisingly, this is going to use some trigonometric functions to find that angle. In particular, the one we're going to use is the inverse tangent function to find the angle, because, well, the tangent function is the one that relates the opposite and the adjacent, and in this case that's what comprises the components of the vector. All right, so let's look at a couple of examples, but here the common pitfall right here is, well, what we need to do here is to be aware of which quadrant is the vector pointing to. So in this case, well, let's draw the vector u negative 1 root of 3. Well, that's going to be the following vector. So negative 1 in the x direction and root of 3 units in the y direction. So in this case, this is pointing the vector in the second quadrant, right? So if we relate this to a triangle, that's root of 3 and negative 1. Of course, you can use the unit circle or the special triangles, of course. And in this case, well, you need to using either one. What do we have here? 120 degrees. In this case, it's the angle using as a reference the positive x-axis, because of course we have another angle right here, but the one that we're going to go with is starting with the positive x-axis. Okay, and in this case, well, theta, the direction is stated in terms of an angle theta, which is 2 pi over 3. Or 120 degrees. Well, it will depend on the application, but mostly for the upcoming ones, which are applications to physics. Well, we want to see the numbers, like the force, what's the magnitude of the force in terms of a number to decimals, etc. Right? Not like radicals. That's more abstract. All right. So for the next example, what do we have? Negative 2, negative 5. This vector will point towards the third quadrant. It doesn't have to be exact, It's not like for the other exercises we had an actual grid, but we needed the grid so you can see the consistency with the addition of the vectors using the triangle or the parallelogram method, so you can check the consistency with the numbers. All right, so in this case, well, we're looking for this angle right here. All right, and well, if we look at these two numbers, negative 2 comma negative 5, well, as opposed to the previous exercise, those are not numbers that are in the unit circle that we can get an exact angle. So in this case, let's just use the tangent function. So tangent of tangent theta. Well, actually, you know what? Let's do the following. To make this simpler, let me get this triangle in terms of positive values, 5 and 2. I know this is negative 2 and this is positive 5. Okay, so, and this is the angle. Let's call this angle alpha for now. Okay, so tangent of alpha equals opposite over adjacent, that's 5 over 2, and alpha is the inverse tangent of 5/2. And while using a graphing calculator, this is approximately 68.20. Let me run it up to 0.20. Of course, you can verify this using your graphing calculator. However, notice this angle right here is only this portion right here, is the 68.20. The angle that we want to find, theta, is 180 degrees. This 180 degrees plus this little portion alpha. In this case, 180 degrees. plus alpha, which is 68.20 degrees, which adds up to 248.20 degrees. Right? And that's where we need to be very careful of where we are in the quadrants. Derek?
Would it be arctan if I had?
Yes, that's what I meant, but not what I wrote. Thank you. Yeah. Inverse tan. All right, so an alternative way to express a unit vector is in terms of its components. Well, it's by representing its components in terms of its angle. And well, if you look at this, if you look at this expression right here, you may find a similarity with the basic trigonometry that you have been doing all your life, So we have cosine going in the direction of the unit vector in the horizontal direction, and we have the sine function going in the direction of the unit vector j. That is, cosine is the x direction, y, and sine is the y direction, like in the unit circle. All those points in the unit circle, the x component is cosine and the y component is sine. But this is for the unit vector. But of course, not all vectors are unit, especially the ones that we are about to work on, those that are applied to forces and physics right here, you'll see. Those are vectors that have a magnitude, whatever that magnitude is. Just any magnitude. Well, you'll see this in action in a second. Okay, so what are the most common application? Forces and velocity. So, and you may have talked about velocity in your Calc 1 course when you saw the physical interpretation of the derivative, So you're given a function that represents the position of a particle, its derivative represents its velocity, and then you talk about the speed, which is really the magnitude of the velocity. We're going to talk about that in a second. And then the second derivative, which is the acceleration. All that is coming back in the later chapters actually, but in the sense of vector valued functions, you'll see how. So, for example, the most common systems, for example, like the first example that we have a little child pulling a sled through the snow on a level path with a given force. All right, and then a friend, I think a second child held to the kid, and it's on the next page. And then we're going to have a combination of forces. When, of course, that combination of forces will give rise to a resultant vector. So let's see this in action. Okay, so a child pulls his sled through the snow on a level path with a force of 50 newtons exerted at an angle of 30 degrees above the horizontal axis. Express the force as a vector. So let's first of all, let's draw an arrow here to represent a vector that's 30 degrees, and let's call this vector V for this force. Okay? And the information that we're given is that the magnitude of that force is 50 newtons. But now we need to represent this vector in terms of magnitude and direction. So that vector V, which is actually the magnitude of the vector times the vector in terms of the direction. And all we do here is the magnitude, which is 50, cosine of 30 degrees, sine of 30 degrees. All right? And cosine of 30 degrees, which is root of 3 over 2, and sine of 30 degrees, which is a half, And let's just distribute that 50 for each component. That's 25 root of, that's 25 root of 3 and 25. All right. So that's what the kid is doing, and by pulling the sled with a 30-degree angle. So it's not, they're not telling it that it's doing it perfectly horizontally with 50 newtons. We will check this result by comparing the resultant force versus the situation if the two combined forces were horizontally. So you can see the consistency of these results mainly. Alright, so let's see. A second child begins to pull on the sled with a force of 30 newtons exerted at an angle of 45 above the horizontal. Draw a picture of the situation, then find the resultant force on the object if both children continue to pull the sled. Okay, so let's draw this using, what happened here? Vector diagram. So what we have here is, so we have the first vector, which is the 30-degree angle. So I'm going to draw it again. And then let's call this vector, V again, the 30-degree. And let's draw the second vector with 45 degrees. Let's call that W. All right. So the idea is that we're going to find the total force, that is the force applied by the first child plus the force applied by the second child's effort. All right. And that's going to give rise to our resultant vector. All right. That's V plus W. Okay. In a very similar way, so all we're doing is putting a situation, putting a story to these operations, right? Well, so let's see about it. Let me rewrite the vector that we got from before, vector V, which is 25 root of 3, comma 25, and the second vector W. Let's start with the actual notation first. So 30, it's also with 30 degrees. No, it's not 30 degrees this time. Oh yes, it's 30 newtons, right? 30 newtons. Whoops. 30 newtons, and that's cosine 45 degrees. Sine 45 degrees. And just beware when you're doing these calculations, make sure that your calculator is in the correct mode, right? Because typically for applications in physics and science, we use the degree mode as opposed to more like the pure mathematics. It's we use everything in radians. We represent results in terms of pi's or radicals, etc. All right, so this is root of 2 over 2, root of 2 over 2. And 30 over 2 in each case, that's 15 root of 2 over 2, 15 root of 2, 15 root of 2. All right, that's the vector W. So what are we going to do? Add the two forces, vector V plus vector W, and just combine these two, 25 root of 3, comma 25 plus 15 root of 2, 15 root of 2. Well, so combine component by component, but I mean in this case we don't have like really nice numbers like the ones we did before. So just for now, just leave them the way they are. So 25 root of 3 plus 15 root of 2, 25 plus 15 root of 2. So that's the vector. That's the vector that describes the resultant force of the two childs pulling the sled, right? But I mean, I feel like this question is a little bit ambiguous because, well, they're asking us for the resultant force. It's not very clear about what do they want in the end. I mean, do they want a vector? Do they want an actual value of a force? Well, we have the vector that describes. That's number one. So the resultant force, well, we also need to express it in terms of its magnitude. So find the magnitude of this vector because we want to know what's the total force, all right, ultimately. And well, that's the square root of 25 root of 3 plus 15 root of 2 quantity squared plus 25 plus 15 root of 2 funky numbers, right? We have these funky numbers right here, but well, we have a calculator. We can do this in our graphing calculator. We should get approximately 79.36. And what would be the units? Just curious about it. Newtons, right? Newtons. Okay. Let's check for the consistency of the result and by relating it to how the situation is going on here. So, what do we have? A first child exerting 50 newtons and then a second exerting 30 newtons. 50 plus 30, that's 80 newtons, right? But that would be if they were pulling exactly horizontally, right? But because they're pulling it at an angle, different angles, both of them, by the way, we should get this resulting force slightly less than the total force if they were doing it perfectly horizontally, all right? Another very typical problem, and this is even more typical in physics, when we have different forces here, the force diagram, Newton's law. So for those of you who have taken physics, you've seen this before. So three forces in different directions are being applied to an object, as shown in this figure. Well, the thing is, the system is in equilibrium when we add the three forces, well, in this case, the three forces or four forces, as many forces as we have, and if the total magnitude is 0. That's what it means that the system is at equilibrium, all right? So, the thing here, well, we're given two forces and an unknown force. That is, by that Newton law, the sum of all the forces for the equilibrium is 0. It has to be 0. All right. We don't know force 3. We can calculate those represent those the forces in vector notation first with the information that we have, and then subtract those vectors from and just to find F3. But need to be very, very careful with the diagram right here. So I know it's very tempting to write for F1 80 times the vector, or rather, yes, 80 times cosine 60, sine 60. But be careful because recall that this force right here is relative to the horizontal, to the positive x-axis, right? And in this case, well, 60 to 180, the remaining should be 120 degrees. All right, and well, the 45, it's still 45. That's fine because that's in the first quadrant. So no issues at all when we have our vectors in the first quadrant, okay? So let's write these vectors first of all. Vector, so F1. vector F1, that's 80 pounds. And I'm gonna skip the units here just so it doesn't look messy, but in the end we're going to get back to the units. Okay, so that's cosine of 120 degrees, sine of 120 degrees. Okay, and again, let me highlight this 120 degrees. Let me explain that again. Why? Because it's relative to the positive x-axis. So when you watch the video again at home, you get to see again, where did I get this 120 from? All right. And that's the first vector, the first force. And simplifying this, we should get negative 40, comma 69.28. So I'm going to give the results only. I mean, everything is just evaluating these trigonometric functions. The second vector, F2, same. The magnitude of 50 pounds. And with an angle of in this case it's itself 45 degrees because it's in the first quadrant. And while cosine and 45, they're both the same, root of 2 over 2. So that's 25 root of 2, which simplifies to 35.36. 35.36. Where did I get that from? Well, this is root of 2 over 2. 50 over 2, that's 25. 25 times root of 2, that's going to give it a 36.36. You can verify that in your calculator. Okay, so we have the two forces. And I mean, if you think about this, it's just like a very simple first degree equation from algebra, you know. So we can solve for the unknown. F3 will be minus F2 minus F1 minus F2. That's or we can factor out the negative. And let me keep the positive here. So F1, which is negative 69.28 plus 36, 36. Okay, and F3 will be negative whatever we get from combining those two vectors. All right, which in this case it's going to be negative 4.64, negative here because negative and a positive, and 104.64. But because we have the negative outside from the solution of the equation for F3, let's get this actually positive 4.64, negative 104.64. So that's the resultant vector. And I mean, it makes sense, right? It makes sense because look at the signs of the components of the result of the another resultant vector. The missing vector, the unknown vector. We have a vector that is positive in the x direction and negative in the y direction. And if you look at the force diagram in the picture, isn't that what we have? Positive and negative. All right, looks good. Yes.
Instead of doing cosine of 120 and sine of 120, couldn't you do negative cosine of 60 sine of 60? Because you're in quadrant 2, so the cosine would be negative.
We could also do that as well. Mm-hmm. Yep. And well, so that's the vector that describes F3. So that's F3. But of course, we need to know the magnitude. So for the magnitude, because we want to know how the strength of that force, well, in this case in pounds. So that's the square root of 4.64 squared plus negative 104.64 squared. And well, using a calculator, this should be 104.74 pounds. All right, so here is where we introduce the unit, where we put the units back. All right. And well, I don't think it's only the force that the magnitude of the force that they're asking us for. They're also asking us for the direction, right? So, and in this case, let's use the same tangent theta equals y over x. Tangent theta equals 100. Let's just use positive numbers if it's fine. Or, well, never mind. Let's use y negative 104.64 over 35.36. And theta will be the inverse tangent of this quotient right here.
Is it a 4?
Yes. Yeah. I don't know where I got that. Well, I think I got it from the previous line, 4.64. And this should be approximately negative 87.46. And well, look at the angle. I mean, even though the picture is not that perfect, it's almost close to negative 90 degrees, right? So yes, this is putting together a little bit of physics, equilibrium diagrams with a little bit of algebra of vectors here. Another situation is velocity, and like we mentioned before, velocity it's a vector quantity because velocity is interpreted with certain magnitude and also takes a direction, right? So what do we have? Let's look at one more example. So we have a plane traveling at a fixed altitude with negligible wind factor. So otherwise, we would be dealing with a really big problem here. Well, so and the plane is traveling at a speed of 400 miles per hour with a bearing of 50 degrees west of north, okay? And the plane then encounters a wind with a velocity of 80 miles per hour in the direction due north. What is the resultant speed and the direction of the airplane? So they're asking to provide the answer to the nearest 10 into one decimal, okay? So let's draw a diagram of the situation. As usual, a Cartesian plane. All right, and so the plane is 50 degrees to the west of the north. So we start with the north, and then from here we go 50 degrees. I know this is not relative to the positive x-axis. In this case, is to the west of the north, right? To the west in the direction of that is to the left, right? And then there is a second vector. There's a wind going exactly vertically because it's towards the north. So let's draw that second vector. And let's label this vector W, and let's label the other one as V. Okay. Well, of course, why not? North. Yes.
Would you put the 50 on the other side since it's based off the x-axis? So it'd be going 50 degrees this way. So it'd be 50 in the bottom part and 40 on the other plane?
Well, that's a good question. So because in this case is it's 50 degrees. I know the wording is weird. It's west of north. So if we the idea is to look towards the north and then from there
Yeah, I see what you're saying.
towards the west. Yeah, I know. I remember when I first took trigonometry and I saw this type of problem, I was wondering the same. Well, why not from the positive x-axis as usual? But then the instructor mentioned that in aeronautics, and that's how they measure those angles depending on the direction. So, yeah. So let's see. We have the information. Okay. Well, actually, instead of let's call it P instead for the plane. Okay. So the vector P for the plane, which has a magnitude of 400, which is the speed of the airplane, and well, in this case, because it's going in a direction diagonal with respect the north. In this case, that's cosine 50 degrees, sine 50 degrees. And in this case, negative 306.41, comma 257.12. Okay. And then we have a second vector W. That vector W is to describe the wind the airplane is encountering, in this case, towards the north. Yes?
Will the cosine 50 and sine 50 want to throw us off? It's like if it was in the first quadrant?
That is a good question, and I have my notes right here, and that was correct. That is true. In this case, when it comes to describing the vector, yeah, don't make this mistake on the homework and on the exam. The same mistake I just did. So that'll be 140. Yep. Thank you. 140. All right. And now to describe the second vector, well, we have a vertical vector with a magnitude of, what is this? 80 miles per hour. And well, it's 0 in the x direction, but because it's going up, let's call this 1 in the well, actually, how about cosine 90 degrees? Just to be clear, where is this 0, 1 coming from? And sine 90. But ultimately, it's the same 0 and 1. It's going to end up being that special unit vector in the y direction, and that's going to be 80 times 0, 1, 80, or rather 0, 80. Okay? So we have the two vectors. Let's add the two vectors together. P plus W. That's the speed of the plane plus the speed of the wind encountering somewhere along the way. That's a negative 306.41 to 57.12 plus 0.80. And this resultant vector should give us, oh wait, no, that's the, hold on, 306 to 57, okay, yes, plus 0.80. And then in the first component remains the same, negative 306.41, comma 257 plus 80, that's 337.112, right? So that's the resultant vector combining the two, this resultant vector, all right? Negative in the x direction, positive in the y direction, just to check the consistency of the calculations with the picture. But well, they're asking for the resultant speed. Well, again, it's not clear what are they really asking, so we need to also express the magnitude of this vector. So To find the magnitude, find the magnitude of P plus W. That's the square root of negative 306.41 squared plus 337.12 squared. And while using a calculator, well, I got 455.6 miles per hour. Okay, so for the direction, well, there's a couple of ways to interpret this situation. Either we interpret, okay, let me first draw the triangle here. It could be north of the west. So that is north of the west. That'll be this angle alpha, like the reference angle, and we get that by doing well, it's actually the whole triangle. Tangent theta equals y over x, which in this case is 337.12 over negative 306.41 and we should get 47.73 degrees. But that is this angle right here, because in this case I'm using the actual signs of the resultant vector. However, if we go back to the original setting that we look at the angle from the y-axis and west of north, it would be the complement of this angle. All right, that is, or subtract this from 90 degrees, this is 42.3 degrees. And in this case, let me note this one right here, in the one in yellow, this is the 42.3 from the y-axis to where the resultant vector is, and this 47.73 would be this vector right here. All right, so it depends. Just be careful on the wording. You may be asked for one or both, right? But it's mostly the vertical axis with the resultant vector.
Can you go over again why tangent theta equals x over 1?
X over 1. Yes. So for the triangle, so that's well, this is, well, let me call this theta. So this is x, y, and r. All right. It's the opposite over the adjacent. That's the trig function. So that's the y over x. This is y, and this is dx. Okay. And I think this is the end of the section, right? I think that's about it.